Hi, my name is Eric Bogatin. I'm a signal integrity evangelist with Teledyne LeCroy. And in this brief video, I want to introduce you to the WavePulsar 40IX, a new instrument for the complete characterization of high-speed interconnects. And in this video, we're going to focus primarily on using the WavePulsar 40IX for S parameter characterization of interconnects. Why do we care about characterizing interconnects at all? Why is that an important issue? In high-speed digital systems, we generally have a transmitter that's trying to drive a signal to a receiver. We've got the die on the transmitter that's generating the signal, and we've got the die on the receiver that's picking it up. Unfortunately, in between the driver and the receiver are all those gosh darn pesky interconnects. In the good old days, those interconnects were transparent. It didn't matter what their electrical properties were. What was important was the connectivity. Unfortunately, those days are long in history for us, because now it's the electrical properties of those interconnects that can screw up the signals. What we have coming out of the transmitter might be these beautiful, wonderful, pristine signals, but in going through all of these interconnects, by the time they get to the receiver, those signals can be grossly distorted. And if your eye looks like this at the receiver, well, the technical term for this situation is you're screwed. What do we do about this situation? How do we assure that the signal at the receiver doesn't look like this? Well, there are generally two important elements to our success in a system design. The first element is we want to get it right the first time. That means you want to design it right so you have confidence it's going to work. And part of designing it right means that we have verified the performance of each of the components, verified that the as manufactured parts behave the way we design them. In other words, that they meet spec. So getting it right the first time is really about characterizing the components that we have received that we're going to use in our system to make sure they meet spec. Unfortunately, sometimes you design your system, you get the components, you build it, and it doesn't work. The signals look like this or are otherwise distorted. If it doesn't work the first time, then our goal is to get it right the second time. And that's where forensic analysis or debugging or troubleshooting comes in. And that's where being able to measure the signals and measure the qualities of the interconnects are so important. Because we want to look at the features of the interconnects, those high-speed electrical performance features of the interconnects, in order to identify where are the weak links, where are the problems originating. And that's where measurement and characterization comes in, to help us in verifying that the parts meet specification, and when they don't, helping us to identify where the weak link is and where the root cause of the problems are. And that's really the value of the WavePulsar 40IX. There are two important innovations that are introduced in this instrument that dramatically simplify the measurements and the analysis. The first is an integration of 3 different measurement and analysis modes in one instrument and one user interface. We can look at the response of the interconnect in the time domain, in the frequency domain, and then with a deep toolbox analyze those measurements to extract valuable information. We'll cover the details of the TDR response and the deep toolbox in later videos. In this video, I want to focus on the features of the WavePulsar 40IX in measuring the frequency domain response, which are the S parameters, as single-ended and as mixed mode. The second set of innovations introduced in the WavePulsar 40IX are related to the measurement process. There are a number of features that are implemented in the WavePulsar 40IX to simplify the measurement process and get you to quality measurements quickly. Some of them are related to the calibration, so there's really no calibration the user has to do. When it turns on, the reference plane is automatically extended to the end of the cable, and the calibration is complete to the end of the cable. There are features that allow you to verify the quality of the connection to the device under test and to change the port labeling to get it into a convenient orientation of what you're used to. And finally, there's a variety of de-embedding techniques that are native to the WavePulsar 40IX. And we're going to review these in one of the later videos when we look at the deep analysis toolbox. Let's spend the last couple minutes taking a quick look at the single-ended and mixed-mode S-parameter measurements of a differential pair and how some of these features that we've talked about simplify the measurement and analysis of the S-parameters. We're going to take a look at using the evaluation board that comes with the WavePulsar 40iX, and in particular we're going to use the top structure over here, which is a simple differential pair. We're going to look at this first in the frequency domain. We'll look at the single-ended and the mixed-mode S-parameters, and then in the next few videos we'll take that same structure and we'll look at it in the time domain, and then we'll apply some of our deep toolbox analysis features to analyze those results. We've just performed a measurement of the 4-port differential pair structure, and we're looking at the results as single-ended S-parameters in the frequency domain and single-ended TDR response in the time domain. As you can imagine, there's a huge amount of data to have to analyze and look at. One of the features of the user interface is the ability to organize the data in a format that makes sense. I've been looking at and analyzing S-parameters for many years, and I have a particular way in which I like to see the S-parameters. On the left-hand side of the screen, I put the frequency domain single-ended response, and on the right-hand side, I put the time domain of the single-ended response. In this short video, we're only going to pay attention to the S-parameters, so that's going to be the left-hand side. First, we're looking at the single-ended response, and then we're going to look at the mixed-mode response. In the upper quadrant, we have the 4 return losses. And you can see, plotted up to 40 gigahertz, the return losses are pretty much the same, except for this one over here. We look over here, this is S21, and you can see that, gee, there seems to be quite a bit of reflected signal, almost minus 2 dB at around 30 gigahertz. It looks like there's some resonance that's reflecting back to us. And 30 gigahertz corresponds to a structure that's about 25 or 30 mils. This indicates that there's some feature on that port, port 2, that we want to pay extra attention to, a large reflected signal from some resonant structure. Otherwise, the 4-port return losses are all pretty much the same. The fact that the return loss is relatively large, minus 13 dB in most up to very high bandwidth, suggests that our differential pair is not a very good single-ended 50 ohm system. We'll see why that is when we look at the time domain response. Otherwise, it looks exactly like we would expect to see. We see the ripples because of having 2 impedance discontinuities some distance apart. A little hard to tell in the frequency domain what those structures are, but we can tell from the ripples that there are some impedance discontinuity structures causing the interference pattern that we see. Looking at the insertion loss and the crosstalk terms, we see some unusual features. I'm going to turn off some of them so we can focus on one at a time. This is just the insertion loss. This is S21. And you notice really large dips here. Where is that energy going? Well, we see that it's not reflecting back. We don't see large return losses at these frequencies. Where could it be going? Remember, our structure is a differential pair microstrip. We send a signal into port 1, we look at what comes out port 2, and we see, oh my gosh, we've lost tremendous energy at 5 gigahertz. Where did it go? Well, in microstrip, we have far-end crosstalk. We send a signal in port 1, and some of that gets coupled and comes out port 4. And so one likely place to look for that energy is in port 4, which is S41. Let's turn on S41, and sure enough, there is the energy coming back to us. This is a feature characteristic of microstrip structures. We see the very large far-end crosstalk. Where we lose energy in the insertion loss, we gain it back in the far-end crosstalk. The second crosstalk term is the near-end crosstalk, and we can turn that on. Near-end crosstalk means we send a signal into port 1, we look at the signal coming out coupling into port 3, S31. And sure enough, it's relatively large because after all, we have a tightly coupled structure. We're talking about minus 13 dB as the amount of coupled signal from port 1 into the near end into port 3. And then one final measurement that we'll take a look at. We have 2 independent single-ended transmission lines. They happen to be tightly coupled. We're looking at the insertion loss going in port 1, coming out port 2. While we're here, as a consistency test, let's look at how similar the two lines are, and let's look at the insertion loss into the other line. We send a signal into port 3, we look at what appears in port 4. So that would be S43. So let's turn on S43. It should be very similar to S21. And sure enough, it is very similar to S21, a few small differences, because after all, the lines are not perfectly identical. This is a quick review of what we see looking at the single-ended S parameters in the frequency domain. Now, let's look at those same S parameters as mixed mode S parameters. One of the key features of the Wave Pulsar 40IX is that we can do all of this analysis of S parameters as single-ended, frequency or time domain, mixed mode, frequency or time domain, all with one acquisition of a measurement. The way we do that is manipulating that measurement into the different formats. And I've created a few predefined setups that will do all of the conversions and all of the display into the format that I'm used to seeing. And those are all available as setup files that anyone can download and use. I have them already built into my Wave Pulsar 40IX. We access them through the file, and we're going to recall a setup. And I have a few predefined setups. The one that we were just looking at was the basic 4-port single-ended, frequency on the left, time domain on the right, and something similar for the mixed mode S parameters. The mixed mode frequency domain S parameters on the left, and the mixed mode time domain display on the right. To take that data and turn it into the mixed mode S parameters, we're just going to recall that setup, and it will automatically calculate the mixed mode S parameters and display them in the way that I like to see. And so here we have the frequency domain mixed mode S parameters and the time domain mixed mode S parameters. We're just going to take a quick look at the frequency domain mixed mode S parameters, and I'm going to show you how I like to see the mixed mode S parameters so that I can do quick analysis of the results. Remember, when we look at mixed mode S parameters, that means that we have just 2 ports for our differential pair. Port 1 can be either a differential or a common port, and port 2 can be either a differential or common port. In the upper quadrant, I'm looking at the differential and common return losses from each of the 2 ports. So those are the SDD11, the SDD22, the SCC11, and the SCC22. These 2 traces here that are almost on top of each other are the common return losses, and what they show is discontinuities that cause the interference pattern and a very high common signal return. That says there's a huge mismatch between the 25 ohm common impedance ports and the common impedance of the interconnect. And that's why we have such a large reflection. Exactly why that is a little difficult to determine in the frequency domain. That's why we're going to be looking in the time domain in the next video. And that's why being able to look in the time domain in one integrated instrument and user interface is so valuable to help us gain insight into why we have that large common signal reflection. The differential return loss, on the other hand, is really low. Look at that, minus 30 dB in the 8 gigahertz and below kind of range, and even up to 40 gigahertz, it's on the order of about minus 15 dB, except for that 30 gigahertz resonance from one of the ports, on port 2. This says that even though it was a terrible single-ended 50 ohm line, it looks like a really good 100 ohm differential pair. Very little reflected signal up to relatively high bandwidth, except for that small resonance. So the return losses for the common signal and the differential signal from the 2 ends looks very good. Let's take a quick look at the mixed mode S parameters for the insertion loss and the mode conversion terms. In the lower quadrant, we have the insertion loss for the differential signal, that's SDD21, that's the teal colored trace. And we have the insertion loss for the common signal. And you can see the ripples in the common signal insertion loss as we would expect, because After all, we have huge reflected signal, and that if it's above minus 13 dB, we would expect to see the impact in the insertion loss, which is exactly what we do. The differential insertion loss is very clean and very monotonic. Remember what the single-ended insertion loss looked like. We had huge dips. It looked like a terrible single-ended interconnect, and yet that same interconnect looks like a great differential pair. And we see that we have very good monotonic behavior, except over here at that roughly 30 gigahertz kind of point. And why is that? Why do we have this little dip? Well, that's because in the return loss, we have a peak. And that energy that's reflecting because of that structure going on port 2 that gives us some of that differential signal reflecting, the fact that it reflects back means it's not getting through. And that's why we have that small dip in the insertion loss. And again, that indicates if we wanted a more monotonic response, if we didn't want to have that little drop in the insertion loss at that frequency, we want to investigate what's going on port 2 to give us that reflected signal. And that's where looking in the time domain might give us a little bit more insight, which we're going to do in the next video. The last two terms that we're going to look at in the mixed mode S parameters are the mode conversion terms. That's going to be the SCD21 and the SCD11. The SCD11 means we send a differential signal into port 1 and we look at the common signal coming back. That's an indication of the mode conversion of sending the differential signal in and getting common signal coming back. And that is the green color. And you can see very little, minus 35, minus 30 dB, even up to 40 gigahertz. Not very much asymmetry in the impedance profiles of the two lines. And lastly, we'll look at SCD21. We send a differential signal in, we look at the common signal coming out. That's usually due to a time delay difference between the P and the N line in the differential pair. And sure enough, we see there is a little bit of mode conversion, up to maybe minus 25, maybe minus 20 dB, and it has the structure kind of what we would expect based on a little bit of time delay difference between the two lines. Even if their lengths are matched, we can still get a little bit of time delay difference in the propagation time of the P and the N lines due to glass weave skew. And to confirm that, we would again look in the time domain at the difference in the transmitted signal, the TDT, of the P and the N line. So that would be S21 in the time domain and S43 in the time domain. And that's one of the things that we're going to pay attention to looking for when we look at the time domain response. So in this quick video, I just wanted to give you a feel for some of the features that we can take advantage of in the WavePulsar 40iX in order to simplify the process of measuring and analyzing the S parameters as single-ended and mixed mode. If your applications involve high-speed characterization of interconnects, I hope you'll take a look at the WavePulsar 40iX. You'll find that it dramatically simplifies the high-frequency measurements that are so important in characterizing interconnects and finding the root cause of problems.